Hello everyone. In today's session, we'll be seeing the contents of week 12, which is the last module of the engineering hydrology course, which is on hydrologic design. In this session, we'll be seeing how to design the storm drainage network using the rational method. So, rational method is one of the oldest method, and it has been used even today for designing the storm drainage system in many places across the world. And we'll see an example related to the rational method, and later we'll be seeing the application of uh, the engineering hydrology course on in designing the storm drainage network, like using the current softwares. Like I'll be showing you an example project which we have done already. So we'll see the application related to that. So in the rational method, we have some of the important assumptions which we need to be familiar with while applying this method to design the storm drainage system. We'll see what are the assumptions one by one. So the first assumption in this method is the maximum size of the catchment is limited to 8 to 10 kilometers square. So for any area which we design, it should not exceed 8 to 10 kilometers square while designing the storm drainage system. So this method holds valid within the catchment size of 18 to 8 to 10 square kilometers. And while applying this method, we need to divide the large subcatchments into small subcatchments while applying this method. So if you say you have this much big area in which you have to design the storm drainage network, we may have to subdivide this entire catchment into small catchments according to the layout of the roads or according to the flow direction of the runoff. So we may have to subdivide this entire catchment into n number of small catchments. That is the second assumption. So we can subdivide the catchment based on road layouts or based on flow direction of the runoff. And the third assumption is that peak runoff occurs when the entire catchment is contributing to the flow. That is, from the remotest point of the catchment, when the runoff comes to the catchment outlet, that is the time when the peak flow occurs. The fourth assumption in the rational method is we are assuming that the rainfall intensity is uniform over the entire catchment, but in reality, the rainfall has the spatial and the temporal variability. But here in this method, it is assumed that the rainfall intensity is uniform throughout the catchment. In the third assumption, we told that peak flow occurs when the entire catchment is contributing to the flow. And I have also written a note that is the time when the runoff from the remotest point of the catchment reaches the outlet. This time is nothing but the time of concentration. So we can assume that this time to be the time of concentration. And during this time period, the rainfall is uniform throughout the interval. That is, it does not, the rainfall is uniform throughout the rainfall duration. Not just spatially, it is temporally also uniform. So the next assumption is the frequency of the computed peak flow is same as that of the rainfall intensity corresponding to the return period of the design storm. So this means that if the design storm which you are choosing is of a 5-year return period, then the computed peak flow is also considered as the 5-year return period flood or 5-year return period flow. But this need not be true in reality. Uh, if you say that 1 in 25-year return period of rainfall happened, the flood that it caused might not be equal to 1 in 25-year return period flood. It can be more than that or even less than that. That depends on the characteristics of the catchment, and several other factors affect this frequency of the peak flow. But here we are considering that the return period of the design storm and the computed peak flow is same. That is the meaning of this assumption. The last assumption is the runoff coefficient is same for all the storms of the recurrence probabilities. So your runoff coefficient is represented by C, which is nothing but runoff by rainfall. So how much fraction of rainfall is being converted into runoff? That is the ratio. And the generation of runoff is dependent on many factors, which we have studied in the infiltration module and the surface runoff module. And typically the runoff coefficient need not be same for all the storms of different return periods. It can vary, and in this method we are considering that to be the same for all the storm events. So next is the procedure. How do we approach when we are designing a storm drainage system? So before applying the rational method, we need to have the intensity, duration, frequency curve, which you might have studied in the hydrological statistics module. So to obtain the IDF curve, I'll briefly explain how to obtain this here. I'm not going into the details because it is out of the scope for this particular subject. So first what we will do is we'll obtain the historical data. So we take 30 years of data. So we will take them in the hourly scale. Now we need to prepare the IDF curves. So we generate the IDF curves like if it is the hourly rainfall. So we have for every hour one, like I'll start numbering. So this starts, let's say, each data point represents on a particular day, it represents every hour data. So starting from 22nd of today's date, we have let's say 7 hours of rainfall, and let's say we are preparing 2 hours. So this is 1 hour, this is 2 hours, then 6 hours, and we can build so on, we can continue. So what we do is we accumulate the rainfall. So let's say you have a precipitation magnitude for 1 hour, it will be same. But when you come for 2 hours, so this will be P1 plus P2, this will be P2 plus P3, P3 plus P4, and so on, it will continue. And 6 hours will be summation of P1 to P6, summation of P2 to P7, and this also will continue. So for different durations, we will find out this running totals. And we will find out the maximum value for each duration. So here we'll prepare the running totals for each of the duration, and we'll calculate and we'll find out the maximum value. So if you say for each duration, we will find out the maximum running total. So for 1 hour, you will have some value, and for 2 hours, you will have some value. 6 hours, you will have some value. And later we will fix a Gumbel distribution or any suitable distribution, and we'll find out the necessary parameters. And finally we will plot the intensity, duration, and the frequency curves. So this will be for 2-year return period. Then let's say this is for 5-year return period, and then this is for 10-year return period, and it can continue up to 100-year return period. And in the y-axis, you have your rainfall intensity, and in the x-axis, you will have the time. So once we get this IDF curve, we can choose a particular duration, and this duration can be your time of concentration for your catchment. And you can select for different return periods. Typically, storm drainage systems are designed for 1 in 5 year return period. So you can find out from this your design intensity. If you have IDF graph, you can directly take it from this. Otherwise, this IDF equation, this IDF graphs can be represented by the equation. So that is intensity is equal to Kt power A divided by time of concentration plus B power N. So here K, A, B and N are constants. So when you fit this IDF curve, you can get this constant, and then Tc is the time of concentration, and capital T is the return period. So once you get this design intensity, then we need to go back to our catchment, and according to the land use of the catchment, we need to choose what is the appropriate runoff coefficient. So your subcatchment may have urban land use, or you will have some vegetation also. Let's say if this is completely urbanized, and here you have some park which has vegetation. So for each of this land use, your runoff coefficient will change. So next step is to determine the runoff coefficients. So next we can calculate the peak flow, that is Qp is equal to C into I into A. Then you will get the peak discharge for the particular design storm which you have chosen. And let's say while calculating the peak discharge, you will be calculating this intensity, and this intensity is dependent on the time of concentration, so which we already know. Now let's say you have a catchment something like this. So this is the first catchment. You have a road in between, and this is a nearby neighborhood. And this is the third neighborhood. And there are this is the intersection point, and there are storm drainage network which is present in this catchment. So I am naming them as A, B, C and D. So when you have multiple catchments, your time of concentration can vary. So what we can do is we need to find out what is the minimum time of concentration. So how to determine that? I'll explain that procedure. So I'm naming this as catchment 1, and then this as catchment 2, this as catchment 3. So the remotest point for the catchment C can be from this farthest point. So this can be the path for the longest path for the runoff. I'm just saying it as a hypothetical situation. So I represented it as TI1. And for the second catchment, it can be from this point until the point A. I'm representing it as TI2. And for similarly catchment 3, this can be the potential path. I'm giving it as TI3. So for the first catchment, we can see you have a drain CB. So if you want to design the drain CB, you need to find out what is the contributing area. So the contributing area for drain CB is only the catchment 1. So all the water from catchment 1 is going to drain to the point C, and then it's going to go to the point B. So first thing is you determine your contributing area. So the entire area of 1. And for this particular catchment, your time of concentration can be taken as a TI1 itself. So there is no problem with that. So your time of concentration is equal to TI1 itself. And once you find your time of concentration, you can find out intensity and you can find out peak discharge. And once you find out the peak discharge, you can calculate the size of the drain that is required using Manning's formula. And after finding out the size, then determine the size for CB. Then once you determine the size for CB, we can calculate what is the time that is required for the runoff to travel from point C to point B. So this is called as the channel flow time. So if you remember from the lectures, the time of concentration can be taken as time taken for sheet flow plus time taken for channel flow, and this is what we are essentially utilizing here. So whatever time TI1, that can be regarded as that can be considered as the time for sheet flow, and from the point C to B, it is going to travel in a channel. So that will come as the channel flow. Now we can calculate the channel flow. So channel flow for the catchment 1. So we know the length of the drain and we can find out the velocity. So velocity, again using the Manning's formula, you can find out what is the velocity. So velocity will be Q by A. Once you determine the size, you can find out this. So we have calculated all the necessary things for the catchment 1 and the storm drainage CB. Similarly for catchment 2, it is going to be the same because we have TA2, and from point A to B we need to find out what is TCH2. So if you write for catchment 2, catchment 2 is drain AB. Contributing area is area of 2. And your time of concentration will be Ti2, and once you get that, you can find out intensity and the peak discharge. Then you will calculate the size of drain AB. Once you calculate the size of drain AB, you can find out time of channel for channel flow time for the drain AB. So that will be length of the drain AB V2. So here it is length of the drain CB. So you will get this. So these two are simple cases. Now let's see how to design the drain BD. Here is what you need to be careful. So if you see the drain BD, the water is coming from the catchment 1, catchment 2 as well as catchment 3. And if you want to find out the time of concentration, it can be from any of the catchment. It can be Ti1 plus TCH1, or it can be Ti2 plus TCH2, or it can be just Ti3. We don't know. So we need to find out the time of concentration for all the possible cases, and we have to choose the minimum of that. So that is the one place which we have to be careful. So contributing area for this drain is all the three are contributing. So here TC can be minimum of Ti1, that is from the remotest point to the point C, and the water has to travel from point C to B. That is the channel flow time, that is TCH1. Similarly for catchment B also we have Ti2 plus channel flow time, and catchment 3 it is directly going to the drain inlet to the point B. So that is Ta3. You need to choose the minimum of these three, and then you can find out your rainfall intensity, then you can find out your QP, then you can size your drain BD, and once you do that you can find out the velocity also if you want. So V3 will be again Q by summation of area in this case. And if you see the formula for peak discharge, it is C into I into A. So if you have the catchment 1 runoff coefficient as C1, catchment 2 C2, catchment 3 as C3, again you have different areas A1, A2 and A3. Either you can do C1A1 plus C2A2 plus C3A3 and then use it directly in this equation, or what you can do is you can find out the weighted average. So this is option 1, and your second option is C1A1 plus C2A2 plus C3A3 divided by A1 plus A2 plus A3. The answer will differ a little bit, but not much. So it's better if you use this particular approach. So everything will be as per the field conditions. And here you can take care of the units also. So the other version of this formula is QP is equal to 1 by 36 C into I into A. In this case, I will be in centimeter per hair, and area will be in hectares, and QP will be in meter cube per second. So this is the approach. Now let's see how to solve one simple problem. This is the storm drainage AB, and this is catchment 1, and this is catchment 2, and both the catchments are drained into the point A. And the properties of the catchment is given. So here we need to design the drain AB, and the properties of the drain is given. So length of the drain AB is 190 meters, and its slope is given as 1.8%. And we need to design this drain for a return period of 5 years. If the designed rainfall intensity So here you have intensity is given by 120 t to the power 0.175 divided by time of concentration plus 27, where I is in centimeters per hour and Tc should be in minutes. And one more information is also given. To find TC, use the Kirpich formula. And here, for the properties of drain, the Manning cell is given as 0.014. We need to design a circular drain, assuming that the drain is at the carrying capacity, so it is flowing full. So let's see how to solve this. So the first step is to calculate the design rainfall intensity, and for that we need to know the time of concentration. So time of concentration is can be calculated by Kirpich formula in this case. This is an empirical formula. TC is given by 0.0185 L to the power 0.77 and S naught to the power of 0.385. So here TC will be in minutes when you substitute length in meters and your slope as meters per meter. And remember that this S naught is not the slope of the stormwater drain, it is the slope of the catchment. Here S naught is the catchment slope. So we have two catchments. Let us find out the time of concentration for both the catchments. So TC will be equal to, I will name it as TC1 into the length of the first drain is the longest path. The longest path for the catchment is 700 meters, and the longest path for the catchment 2 is 250 meters. So 700 meters for the first catchment, and the slope for the first catchment is given in terms of percentage. We are just going to divide it by 100 so that it becomes a meter per meter, and this raised to the power of minus 0.385. So TC1 will be 25.35 minutes. Similarly for catchment. This is 10.53 minutes. So now we've got the time of concentration. Let's go to the catchment diagram. So if you see for the drain AB, the contributing area is from both catchment 1 and catchment 2. Here we don't have any channel flow. It's directly going to the point A itself. The next thing is we need to find out which is the minimum time of concentration, and we have found out that the catchment 2 has the minimum time of concentration. So your design time of concentration will be minimum of TC1 and TC2, that is 10.53 minutes. Now you can calculate the rainfall design rainfall intensity, that is given by 120 into your return period is given as 5 years. This raised to the power of 0.175, and time of concentration in minutes plus 27. So this gives you 3.037 centimeter per hour of rainfall intensity, design rainfall intensity. Now we can calculate the rational method, peak discharge using the rational method. So QP is given by 1 by 36 CIA. Here we are having two catchments, so I am modifying the equation a little bit. Design rainfall into summation of phi is equal to 1 to n. Okay, name it as J to avoid confusion. Cj into Aj. So QP is equal to 1 by 36 into design rainfall intensity is 3.037, and I am going to expand this. So C is 0.4 and the area is given in kilometer square. We can convert it into hectares. 0.16 kilometer square into 10 square will give you the hectares, plus 0.6 into 0.08 into 10 square. So this will give you the peak flow 0.9448 meter cube per second. So once we get the peak flow, we can use the Manning's formula to determine the size for the drain loop. So QP is equal to A by N, R to the power of 3 by 2 by 3 and S to the power of 1 by 2. So here we need to design a circular section, and condition is given as full capacity. So when a circular drain is flowing full, your hydraulic depth, which is the ratio of wetted area to the wetted perimeter, is D by 4, which you might have read in applied hydraulics. So we can find out pi d square by 4 into Manning's n, and this is another d by 4 to the power of 2 by 3 and S naught power half. Now we can substitute all the known values. Only unknown value is the diameter of the drain. Manning's M is 0.014. And the slope of the drain, it is given as 1.8 percentage. So if you solve this, you will get 0.649. We can approximate it as 0.65 meters. So this will be the diameter of the drain AB. And once you get this, you can find out what is the velocity. That is optional. So as per the design guidelines, your velocity should not exceed 3 meter per second, and your velocity should not be less than 0.6 meter per second. This you might have studied. This is called a self-cleansing velocity. And the maximum velocity is 3 meter per second. If it is exceeding, we might have to change either the slope of the drain, or we might have to do some dimension changes. That will come with respect to the site constraints. So this is with respect to the rational method. If you have any doubt, you can ask me. So determining the time of concentration for the given catchment, this is one of the crucial steps which you need to remember. First, we need to find out what is the contributing area, and we need to find out whether the catchment has a sheet flow and channel flow to the point of interest where we are designing, and we can find out the time of concentration. Okay, let me share some of the practical applications. So if you see in this, this is one of the case study which we made for an area in Chennai. So here the problem was we had to realign the storm drainage network. So you can, if I zoom in, you can see what is the. You can see these are the different catchments which we have, and if I further zoom in, you can see where it is draining. So this particular catchment is draining to this node, and this line is a storm drainage network, and we have the entire model. And this is a design storm which is having a 2-year return period of 24 hours. And if I further move, this is the outlet for the entire area. So the inverted triangles are the outlets. So this is how we represent it in the software. This does not use the rational method, rather it uses advanced methods which is available. So I'm just going to run this model and show how the flow happens to give you some idea. So you can see the profile of the stormwater drain. This is the longitudinal section which we have considered, which we have designed. So this is how longitudinal section will look like, and we have the varying sizes throughout the entire stretch of the channel. And if I animate it, you can see how the water level is varying with respect to the rainfall which happens as the input. So the rainfall intensity increases slowly and then it reaches a maximum. So this is how typically flow takes place in the drain. And the rainfall is receding right now. So this is one example where we had to design a storm drainage network. And there is one more example. So this is the model for entire IIT Madras which we have made. So if you can see, this is the entire watershed area. So if you see on the left side, these are all the Gindi National Park, which is next adjacent to our campus. And we have the water coming all the way from that catchment into the campus. And then it comes to the lake which is within the IIT Madras. There are 2 lakes and 1 marshland. So these green color points are the lakes, and outside the catchment we have another contributing area. This is outside the campus. So this is where we apply the different whatever you have studied. We apply routing, then we use the design storm, we use the return periods, and we apply all sorts of the modules which we have studied separately in this entire course. We apply everything together in this software. And here we can see how the water is going into the lake. So this is the one of the lake which is about 4 to 4.5 meters depth, and we have the small drainages within the campus, and you can see how it's filling with respect to the rainfall. I'm simulating it for a 1 in 2 year design storm. You can see some channels are getting flooded, but this is the existing condition that is inside the campus. And you can see the lake level which is increasing and then later decreasing once it is full. So these are some of the practical applications, and we have one more software which is called as the HMS. So this is the entire watershed analysis. Here we'll be using this software. We will find out the we will do the hydrological modeling, and later it can be used for flood modeling also. So these are some of the advanced software which, if you are interested, you can explore this, and it's all open source software. You can use this. So I hope this course was interesting to you, and this sessions were helpful for you to solve all the some of the problems, and I hope it will be useful for competitive exams also. If you have any further queries, you can ask me. So if you have no further queries, I'm stopping the session. Thank you.